Blockchain as a technology has many advantages like transparency, immutability, and censorship resistance. To gain the benefits from all these properties, we have to change our design principles for user applications and services. Web3 applications should work in a slightly different way, not like the regular web services of Web 2. Let's take a closer look. Traditional web services have server and client elements. When a user opens a page in his browser, the server responds with a web page with static content like HTML, various assets like images and fonts, and JavaScript code. Once the user interacts with the UI components of the web page, for example, buttons and forms, the JavaScript code creates a new request to the server to fetch data to display or to write some data to the database on the server. The server processes the request and returns as a response HTML, XML, or JSON data. The JavaScript code in a browser uses this data to change the client's application state and view. Web3 works in a different way. Of course, a Web3 app also requires HTML and JavaScript code to run in a browser. So the logic of server and client are still needed. A read request is created when a user interacts with a client application. In a Web3 app, the request is processed by a node from the blockchain network. The main difference here is that the data can be read by anyone and is public on popular open distributed ledgers. The most important thing is to know how to write a piece of information into the blockchain network. Here we use the terms transaction and digital signature. All updates to the blockchain network must be submitted using transactions. The blockchain network determines that a transaction is valid only if a valid digital signature is provided. You may not be familiar with digital signatures, so let's dive deeper into it. Imagine that Bob creates two keys, a private and a public key. These keys are connected by a mathematical formula in a way that for each public key, there is only one private key and vice versa. When Bob creates a message or transaction, he signs it using his private key. Bob must keep his private key secret, but Bob can share his public key with anyone who will validate the signed message or transaction. Anyone with Bob's public key is able to verify that a certain transaction was signed by Bob's private key, so verifying that Bob was the only one able to create and sign that message or transaction. This is known as asymmetric cryptography. Here is an important note. A private key can be generated from some random seed phrase using, for example, hashing functions. The public key is obtained from the private key by using an elliptic curve multiplication. The network address, on the other hand, is obtained directly from the public key by using hashing functions. All these transformations are one-directional. The opposite direction is very hard in terms of required computations. Actually, it implies an astronomical value of computations required. Seed phrases usually look like a random list of words, usually 15 or 16. You can see an example on your screens. So seed phrases and private keys must be stored securely. But at the same time, they should be easy to use in order to sign transactions, right? The main software of the web is a browser. So the best solution is to keep seeds and private keys in browser extension applications. Browser extensions are secure by design. Web pages do not have access to extension storage and only can make requests to it. At the same time, they're convenient for users and developers because of the web extension standard. The main idea is that third-party application developers will not request that users use their private key directly with their apps, so they don't expose their sensitive data to the web. Many blockchains have browser extensions as secure key storage and as a tool to sign transactions. In the Waves ecosystem, there is Waves Keeper for those purposes. Here's what the workflow looks like. users store their private keys in a browser extension. Third-party applications, like wallets and decentralized applications, can request an extension to sign a transaction. When apps request something, the user sees it and can approve or reject it. If he approves it, the transaction goes to the blockchain network. Well, let's summarize this lesson and the most important things we've learned. We talked about digital signatures and how they affect user experience with Web3 services. Also, we have talked about browser extensions and WebsKeeper. In the next video, we'll talk about the very first and one of the most important use cases for Web3. We'll talk about money, currencies, cryptocurrencies, liquidity, and some other interesting topics. See you in the next video.